So now let's take a look at example number 2. And I want you to try this one on your own. Can you use a linear approximation to estimate the value of the natural log of 1.5? Now remember here, what you're going to have to see is that I'm asking you to compute a very difficult value, and you need to come up with a way that you could identify that I'm working with a particular function with a difficult number plugged in. And could you instead come up with an easy number to plug into this function that's close by? So take a moment, try to think about it, and you can use what we did in the previous example to try to help structure your thinking at least a little bit. Go ahead, pause the video right now, try to play around with this for a moment, and then when you unpause, you'll see me work through the solution. All right, well, hopefully you actually did go ahead and try this out. It's not always necessarily a super easy thing to do on your first time through, but let's see what we could have done here. What I could have seen is that I'm working with a function kind of like a natural log of x, and I'm plugging in the difficult value of 1.5. Pictorially, I kind of have something that looks like this. My natural log function, I know, goes like this. Here's where the value of 1 is. And so 1.5 is difficult. It's maybe right here. And I'm going to get this y value. This is the one I'm looking for. What is that output? So an easy value that's nearby, where I could build a tangent line, might be at 1, because I know how to find the natural log of 1, even though I don't know how to find the natural log of 1.5. And then, of course, the idea is, once I find this linearization, I can go ahead and plug 1.5 into my blue tangent line, and I'll get a y value that's not the same as what I was looking for, but pretty gosh darn close. So I'm going to go ahead here and state that we want a tangent line at x equals 1. So I can see here that we note that f of the value of 1 is equal to natural log of 1, which is 0. So I can start to see that I'm getting a point shaped up there. And I know that f prime of x is equal to 1 over x. And so that means that f prime of 1 is 1 over 1, which is just 1. And so I can see that I have a point of 1 comma 0, and I have a slope of 1. And so my tangent line could be written as y minus 0 is equal to 1 times x minus 1. Or more simply, this is y equals x minus 1. To write it in our linearization format, instead of saying y, I would just say L of x. Does it really matter? Not at all. You could use either of these forms. Both of these here, of course, are the same line. I've just labeled them differently. So once I have this, now I can go ahead and start to try to provide an approximation. I can now say that if I am interested in calculating the natural log of 1.5, this is roughly the same as this is the same as calculating f of 1.5, but that is calculating 1.5 plugged into my black function. And what I notice is that's roughly the same as going to my tangent line and plugging in 1.5. But going to my tangent line and plugging in 1.5 is super easy. I don't need a calculator for this at all. I can just go ahead and say 1.5 minus 1 is equal to 0.5. So I would guess that the value of the natural log of 1.5 is actually just 0.5. Again, this value here is roughly the same as 0.5. Now, the other thing I could probably tell before even looking at my calculator to kind of compare and see how close my answer is I can probably guess whether this is an overestimate of the correct value or an underestimate. And again, I can easily determine that by just looking at the picture, because I know that I just found, again, 1.5 plugged into my blue line. I reported that y value back as my answer, whereas I know that the real value is a little bit lower. And so I can easily state here that this is an overestimate, and I can just easily tell that from the picture. So I would predict that when I go to my calculator and I type in natural log of 1.5, I'm going to get something a little bit smaller than this value. Now I'll leave it to you to go ahead and check this value on the calculator, but I'm very confident that I'm right in stating this is an overestimate.